In this example, we're going to do a repeated measure t-test. I've already set up the data, very similar to the previous t-test demonstration. In this case, we have a before and after score. The mean for the before score is 9.71, the mean for after score is 12.71, and then the standard deviations for those two conditions as well. Almost 2 for before and just over 3 for the after. Degrees of freedom would be the number of pairs that we have, the number of participants, minus 1. I set it up to use the count function, so count the number of observations between B2 and B8 and subtract it 1. This is where things change somewhat from the previous example. We can still use a t-test function and look at our array for the before and our after scores. And we can select a two-tailed test. But now, when we select type, we have to select a paired sample t-test to do the correct analysis. A paired sample t-test will give us the equation that we would use to do a repeated measure t-test. So instead of putting in a 2, as in the last example, we'd enter 1. That's the probability of committing a type 1 error with this particular test. Now we need to go back again and get our t-value. We would use the same function again, t inverse, and when we do that, we take our probability, which we just calculated in B14, and the degrees of freedom in B12. And our t-value is 2.26. Now, with this t-test, with 6 degrees of freedom equaling 2.26, we would conclude here that this is not a statistically significant difference between the before and after scores. In order for us to say that it's a statistically significant difference, we're going to need to have a probability number here of 0.05 or less, where that 0.05 corresponds to the alpha level that we use as a standard in our test. Anything 0.05 or below, we would say that the differences are significant. Anything above 0.05, we're going to say that they're not significant. So in this case, our t-test is not significant.